Sorry, one second.
Oh, good. Take your time.
It might have been on problems.
Might have been on what?
Might have been on complex 16IB problems. Let me see.
I'll pull up 14, 15. It's in 14, 15, or 16, right?
Yeah.
Okay. Here's 14. This one is a geometric sequence one. This one, I think you're referring to.
Yes, that was.
Okay. All right. I'm gonna copy this and put it into Paint just so I have some more room. Actually, if Microsoft Whiteboard cooperates, then I might even use that because I think Whiteboard is better. This is a paper 1 problem, so you're not going to get calculator. However, I think it's not too bad. You just have to go back to have a fundamental understanding of the definitions, and if you can work through those well, I think you should be fine. So the main thing you want to remember is with the definition of a geometric sequence is that you have a common ratio R, right? Successive terms, if I divide one term by the preceding term, the term that came just right before it, then I will get some number R. And then if I divide the next term by that same term, then I'll get R again. That's kind of the definition of, this is physics. This is not, hold on, let me open a new board. That's the only problem with whiteboard, it takes a long time. And then of course, I think with arithmetic sequence, it's the same idea, except it's a common difference, right? There's that idea of that common trait, that common difference or common ratio. Okay, all right. So if we look at part 1, part A, the geometric sequence has complex terms, and it's defined by U, okay? UN plus 1 is equal to 1 plus I. I know I'm just rewriting it, but usually I have to do that. UN, and then the first term itself is 3. What does this tell us? What this tells us is that the first term is 3, and then here, oh, sorry, this is a geometric sequence. It's not an arithmetic sequence. It couldn't be. What this tells us is the next term is 1 plus I times the current term. So if I wanted to express this as the common ratio R, I know by definition the common ratio R is U sub n plus 1 over U sub n, and that's going to equal 1 plus I, right? So I know that that's my common ratio. So that from this, I can actually create an explicit formula. U sub n is going to equal 3 times 1 plus I to the n minus 1. This is how I like writing it, just so I have an explicit way to express that. Now, they're asking us to find the 4th term of the sequence. So if we want to find the 4th term, we're trying to find U sub 4. That equals 3 times 1 plus I to the 3rd power, because we're trying to find, right, 4 minus 1 is 3. Now you just have to use binomial theorem to expand this out. You're going to get 1, you'll get 2i here, and then you'll get, no, that's absolutely wrong. 1, you'll get 3 I here, then you'll get plus 3i squared, which is minus 3, right? And then you'll get plus I cubed, which is minus I. And then now you expand this out. 1 minus 3 is negative 2. You'll get a negative 6 out here. And then you'll get a 3i minus I is 2i. 2i times 3 is 6i. So negative 6 plus 6i. Do you have the solutions open? I just want to make sure I'm not, because if I start wrong, it'll end up wrong. I'll have this open on the side just so I can check and make sure. Negative 6 plus 6i, that's correct. Okay. All right. Now for part B, we want to find the sum of the first 20 terms, okay? We're trying to find the sum of the first 20 terms. This is a formula. Do you have, I sent this in the Slack. Do you have this? It's from Revision Village. It's a one-page formula chart. If you look under number and algebra, it says that the sum of n terms of a finite geometric sequence. If it was infinite, do you know the sum for infinite geometric terms? It's 1 over, what is it? It's U1, right?
I think.
It's u1 over 1 minus r, I think. Yeah, and obviously the absolute value of the ratio has to be less than 1. But if you have a finite number of terms and you're trying to sum them up, the formula, you can derive this, but they gave it to you in the formula sheet. So you know it's u1 times 1 minus r to the n over 1 minus r. Okay, so that means if we're trying to find the sum of the first 20 terms, that means I want s of 20, right? Now I'm going to plug in my terms. U sub 1 is 3. 1 minus, the common ratio is 1 plus I, right? 1
Yeah.
plus I to the n power, so n is 20, okay? And then we have 1 minus 1 plus I in the denominator, correct?
Mhm.
Okay. Oof, this looks interesting. How can we do this? Well, first of all, you'll notice that in the denominator, you'll just get a negative I, right?
Yeah.
So in order to get rid of that imaginary, there's a very, it's a very funny joke is, I don't like to be on the bottom. So it's that's how mathematicians remember to, multiply by I and get rid of the I in the denominator. So if we have negative I right here, to get rid of that negative I can just multiply by I. And if I do that, I have to do that to the top. So then I'm going to get 3I times 1 minus 1 plus I to the 20 power, right? And then in the bottom, I get I squared, which is negative 1. Negative, negative is positive. So I don't have a denominator anymore, which is nice. Now, the question is, how do we evaluate 1 plus I to the 20 power? What do you think? I think I know how to do that. What do you think the best option is? So when you
I was gonna.
oh, go ahead.
Every time I talk, it's loud. It's
Echoing,
like my
yeah.
echo. Okay, so maybe like what's it called? Like 1 plus I to like a certain power and then that to another power.
So when you're doing that might be an okay approach, but I think there's an easier way to do it is, when you have small powers of I and you have it in rectangular form, it's easy to multiply it out, right, and get the answer. But when you have bigger powers of I, it's easier, I think, to write that in exponential form. Because 1 plus I is going to equal root 2 e to the I pi over 4. Sorry, I pi over 1 plus I pi over 4, right?
Yeah.
So this, whenever you have large powers, you're not gonna. There's no way they expect you to expand that. That's ridiculous, right? It just doesn't make sense. So the likely option is going to be to go ahead and write that in exponential form. If I write that in exponential form, I'll get 3I times 1 minus. If I do this, what am I going to get eventually? I'm just going to do this in one step. If I raise this whole thing to the 20th power, I'm going to get 2 to the 10 here, right? And then I'm going to get e to the I pi over 4 raised to the 20. 20 over 4 is 5. E to the 5 pi I, what would that be? 1, 2, 3, 4, 5. So e to the
5 pi would be e to the 4 pi would be 2 complete circles and then half. So okay, e to
just
the
pi, right? Because
pi.
1, 2, 3, 4, 5. Yeah. And then we know that e to the pi is on the negative real axis, so I can just get rid of that and make that a plus here, right? And that actually, I think, is our answer, because we've given our form in a times 1 plus 2 to the m. So our a is 3i, and they said that a could be part of the complex. It can be a complex number. It doesn't have to be a strictly real number. And m is part of z, the set of real integers. So yeah, we've met the condition, so we can stop right there. Okay, now it says I'm going to erase part A and B, because I think we'll need some of this stuff up here, but we're probably not going to need A and B anymore. Okay. All right. So for part C, we have V of n. V of n is U of n times U of n plus k. Okay, so how I do this generally is I would just go ahead and multiply UN out and show that it matches the form of a geometric sequence. However, the proper way to do it is to say that, by definition, what did we say a geometric sequence has to have?
Common ratio.
Common ratio. So that means the common ratio, it has to be consistent. The next term, the ratio of n plus 1th term over the nth term has to be constant. So if I do v of n plus 1 over v of n, what's that going to be? That'll be u of n plus 1 times u of n plus 1 plus k over v of n times v of n plus k. I'm sorry, u of n times u of n plus k, right?
Mm-hmm.
Make sense? Okay. Now, u of n plus 1, we found out already here, they gave us, it was 1 plus I times u sub n. And if I just plug in, okay, this is n plus 1 plus k. How can we do that? Oh, we can just plug in n plus k here, right, into n. That'll give us n plus k plus 1. That'll be 1 plus I times u of n plus k, essentially. Make sense what I did?
Yeah.
Okay. And on the bottom, we have un, and we have un plus k. Un cancels. Un plus k cancels. We get 1 plus I times 1 plus I, which is squared. 1 plus I quantity squared, it's a constant term, right? I is not a variable here, it's just it's the imaginary unit. So this is, which is constant, therefore geometric series. You can say GP. It's not series, GP means geometric progression. Okay. Now, okay. So now for part D. Hi, Samhitha. Okay. So now for part D. No, we just did part 1, right? We need to do the other 2. State the first term. What would the first term of this sequence be? How could we figure that out? Well, we can just plug in V1, right? V1 equals U1 times U1 plus K, right? So if we do that, what do we get? We get U1 we know is 3. And what is U1 plus K? U of 1 plus K would be, oh, sorry. Is that the best way to do this? That's probably not the right way to do this, because I don't know how to deal with a K, right? I don't think that's the right way to do this. What I would do at this point is go ahead and multiply these out. U of n is going to be the 3, this term right here. So 3 times 1 plus I to the n minus 1. And then u of n plus 1, n plus k would be 3 times 1 plus I to the n plus k minus 1. Is that correct? So in that case, what we were doing before would also work, right? We're essentially doing the same thing. We're just plugging it in at this point. So if we want the first term, let me know if I'm getting confusing, because this is a long chain of thought to process. So V1 is going to be 3. If I plug in a 1 here, that becomes a 0, times a 3. If I plug in a 1 here, that just becomes a k. So I'll get 1 plus I. Oh, I do not want that to autocorrect. 1 plus I to the k. So then I get 9 times 1 plus I to the k. And I think that's the best we can leave our answer because we don't know what k is, right? K is just an element of the set of natural numbers. Does that make sense, Maham?
Yes, I think.
Just plug it in, really. That's what we're doing here. To find the first term, we just plug in 1, n equals 1. Okay, now show that the common ratio is independent of k. Well, we already found the common ratio. We already found so this was part 1, this is part 2. Now to find part 3, we already showed in 1, common ratio r was 1 plus I quantity squared, right? And what is that? That's just going to be 1 squared plus 2i minus plus I squared, which is minus 1. So these will go away. The common ratio is 2i, which is independent of k, as required. That's what they asked us to show, and we've shown that. Okay. Make sense? So here it's just a matter of substitution, really. It's just a matter of plugging it in and then checking whether it works or not. Okay. The last one in this portion is a sequence Wn is defined by Wn equals absolute value of, or modulus in this case maybe, of Un minus Un plus 1. Show that it's a geometric sequence. Once again, how are we going to show that it's a geometric sequence? What's the definition?
Common ratio.
Common ratio, right? So if we take Wn plus 1 over Wn, this might not be the smarter way to do it, but let's just try and see what happens. Well, we're going to get Un plus 1 minus Un plus 2, right, over Wn, which is Un minus Un plus 1. Okay. Now, Un plus 1, by definition up here, is going to be 1 plus I times Un. And then here I'm going to get 1 plus I times n plus n plus 1. But then we already know what Un plus 1 is, and so it's really a recursive formula that we're applying here. So I can just plug Un plus 1 again back in. And this will be 1 plus I times Un, and then all of that over Un, which is 3 times, or I'll just leave it in the form Un, because I think Uns will cancel eventually. Un minus Un plus 1 is just formula up here, which is 1 plus I Un. Okay, now we can probably factor a Un out, right? If we factor the Un out, these are all going to go away, right? So now what we're left with is 1 plus I minus 1 plus I times 1 plus I, which we found out in part 3, I believe, was 2i. Okay? And then on the bottom, we get negative 1 plus I, but this is modulus, so you can just write 1 plus I. And then in the top, we're going to get I minus 2i is negative I, so we'll have 1 minus I on the top, then 1 plus I on the bottom. And if you find, what's the modulus of the top?
2.
Square root of 1, square root of 2. That doesn't look right. Common ratio can't be 1. What did I do wrong here? That doesn't seem right, does it? Okay, we start off with the next successive term over initial term. Un plus 1 minus Un plus 2, because we did n plus 1 here. N plus 1, n plus 2. Un minus Un plus 1, okay. N plus 1 is 1 Un minus 1 plus I times Un plus 1, and that's 1 plus I times Un over Un minus 1 plus I times Un. Then we factored out a Un, cancel those. That's a 2i. That's weird. Why would that be? See, this is the case where I wouldn't do the successive terms. Maybe I did something wrong here. It might just be that. But for me, if I can write this out explicitly, right? UN I already found out. What was UN? UN was simply 3 times 1 plus I. 3 times 1 plus I to the n minus 1, right? I already found what that was, and then I subtract u of n plus 1, which is 3 times 1 plus I to the n power. Now, if I do that, I think there's a benefit here is now you can easily see what to do with this. You can, if you just simplify this really at this point, you're gonna get 3 times 1 plus I to the n times 1 plus I to the minus 1 power minus 1. Okay. Now the modulus of, if we can take the moduli individually is what I'm saying at this point. We can pull out the 3, right? And then we can take the modulus of 1 plus I to the n power. Okay. And then we can take the modulus of 1 plus I to the negative 1, which is essentially 1 over 1 plus I. And then we can subtract 1. If we do that, what happens is the modulus of 1 plus I is root 2 to the n. And then 1 over 1 plus I, we can do that off to the side. I don't want to be in the bottom, so we multiply by 1 over 1 minus I. 1. That's a joke mathematicians use to remember not to put I in the denominator. But anyways, in the bottom we're gonna have 1 squared minus I squared, which is 1 squared, I believe. So, right? Is that right? 1 squared minus I squared. I squared is negative 1, so that should be 1 plus 1 plus 2. So 1 minus I over 2. Okay, so now what's the modulus of this number here? The modulus of this number here is going to be the square root of 1 over 4 plus 1 over 4, or it's really just 1/2 root 2. Okay, so if I write this out, what happens now is I get 3 root 2 over 2 times root 2 to the n. Now, to get a geometric sequence, I want to write it in the form some first term, so w1 times r to the n minus 1. So if I want to write it in the form n minus 1, root 2 to the n minus 1, then all I have to do is just think add plus 1. And if I add plus 1, that's like multiplying this entire thing by root 2. If I multiply by root 2, I'll get 3 root 2 over 2. Root 2 is 2, cancels, and I get 3 times root 2 to the n minus 1 power. This is how I would do it, because this shows you explicitly that it's a geometric sequence because it matches the form. And now I can say that therefore, this is GP, it's geometric progression with W sub 1 equals 3 and common ratio equals root 2. I have shown here that the common ratio is root 2 simply by putting it in that form. That's my argument. I don't think you have to do the method where you take one term over the other. But that's definitely a helpful definition. It does help in certain cases, I do think. It just depends on the scenario. So you have to really think about it and be careful about, where to apply what. And finally, the last part of this question is a more conceptual question, I think. And it asks, state the geometrical significance of this result with reference to points on the complex plane. Okay, what's the geometric significance of this result? Well, that means, okay, what is Wn? Wn is u sub n minus u sub n plus 1, and I'm taking the modulus, which is like the difference, like the distance, right? So if I have the distance between points in u sub 1 represented by Wn, and Wn is a geometric sequence, that means geometric sequences are increasing over time, right? They're very, right? They're very quickly increasing. That means the successive differences between the points in u sub u sub n are going to be modeled by a geometric sequence. That's what that means for part 2. Okay, I think that's a complete solution. Hopefully that makes sense. Is there anything on here that's still unclear? It's just a lot of algebra, really. It's just, you want to be really careful with your algebra and make sure you don't, because if you make a mistake, it'll mess up the rest of the thing. And of course, there's error carry forward. So don't worry. If you make a mistake, you make a mistake. But, just be really careful with what you're doing and take your time. I think what I've noticed, again, we've talked about this in the past as well, is when you try and rush on these problems, it doesn't end out well. It really doesn't end out well if you try and rush. It makes more sense just to take your time, think about what you're doing, and get to the right answer. Okay. Any other IB problems you wanted to take a look at from what we've done in class? No? Okay. In that case, I'm going to go to IB documents and do, let's see. Okay, I'm going to do one problem at random from 1.5, then 1.6, 1.7, 1.8, probably not 1.9 because that's systems of state linear equations. Then we also need to do polynomials, right? Polynomial functions and their graphs, and then maybe 2.5 and 2.6. If you need to leave early, that's perfectly fine. I'll just go through one at random for each. So let's start with 1.5. Okay, there's a lot over here to work on. So just pick one at random, whichever one looks like you might want to do. Is there a certain type of problem you think you would want to work on? Out of these, anything that looks appealing or looks like it would be interesting to work out, or no?
I can look really quickly at the problems and see if there's one type of problem in specific that I had across the board a hard time doing. Um, I'll just click on just like one random IB problem. Um,
And I'm not going to do any of the 14, 15.
any of them that use trig rules.
Trig rules. Okay, interesting. So I think I actually did one today, and it's on the PowerPoint. It's from number 11. This one will take a pretty big chunk of time if I try and do number 11, but I think it's worth it. It's from 2017, I believe. From 2017, and number 11 on 2017 uses so many trig rules. So this will take a while, but let's work through it and see what we can come up with. So once again, your good friend is your formula sheet over here. If you don't have that formula sheet, you're really going to struggle. I mean, unless you just use these formulas every day, which I don't think many of us use these formulas every day. So it's really helpful to have them. Okay. Okay, number 11. Also, by the way, did you guys understand this problem when she was doing it in class? Like, she just touched over it because I was really confused by this one for a second. But then I think this is a geometry problem. The geometry problems, I think, for me are the trickiest. Okay, we're going to take a look at number 11 here. It's a 22-mark problem, which means it'll probably take us about 30 minutes to get through. So this will take us a while. Just wanted to brace you for that. And from the very beginning, we're going to be using trig rules. So this is exactly what you wanted. Okay. Oh, that's not the right one. Am I pasting the right one? I'm still not pasting the right one. Did I even copy it to begin with? I don't think I copied it. Here. Make sure to take a screenshot. Okay, there we go. Okay. So if we want to solve this first one here, Trig equations are very hard to solve unless you apply properties. This first one here, part A, says solve 2 sine of x plus 60 degrees equals cos of x plus 30 degrees. Immediately, right off the bat, I know I cannot deal with sine and cosines altogether. That's very tricky to do. I think that's like, it's, I don't know, I definitely don't know how to do that. So what would I do? Well, one thing you can do is turn this into a sine. And to turn that into a sine, what you could do is express this as sine of 90 minus 30 degrees plus x. This is a property that's, because right, cosine literally means it's the complement of sine. So if I take that angle and subtract it from 90, that'll give me the sine function. That's one way to do it. Another way is, I think that's what the mark scheme does, is to directly start with properties. That might be the easier way to do it. So do you know, Maham or Samhitha, do you guys know the sum or difference formulas?
Um, no, honestly.
Okay, that's
I
okay.
I have a paper with them, but I don't.
Yeah. So that's, and you have them on here, so it's fine. But sine of a plus b, or alpha plus beta, is sine alpha. And I'm not going to write out the formula here just because it'll take too much time, but you kind of want to like use it enough where you're kind of familiar with it. So it's sine alpha cos beta, where this is alpha and this is beta, by the way. I refer to the first angle as alpha and the second angle as beta. So sine x cos beta, so sine alpha cos beta, plus cos alpha sine beta. So this will be sine 60 degrees. And then on the right-hand side, we're going to have cos alpha plus beta is equal to cos alpha cos beta minus sine alpha sine beta. So this will be cos x cos 30 degrees minus sine x sine 30 degrees. Okay? Now, some of these you can simplify. Do you know what cos of 60 degrees is? What is cos of 60? That's 1/2, right? So this will be sine x over 2. What's sine of 60 degrees? That's root 3 over 2. This is going to be root 3 cos x over 2. Okay? And on this side, cos of 30 degrees is root 3 over 2. So you're going to have root 3 over 2 cos x. And then you'll have sine 30 degrees, which is 1/2. You'll have sine x on 2. Okay. Now, if you can get rid of these denominators here. You'll get sine x plus root 3 cos x equals root 3 on 2 cos x minus sine x on 2. Now, what I would want to do is probably bring all the sines to one side and bring all the cosines to one side. Why do you think I would do that? That's more important, understanding why we would do that. Because if you remember this, you can solve these types of problems. Why would it be beneficial to move all the sines to one side and then move all the cosines to the other side?
I mean, wouldn't it just work better because you're working with the like similar terms, sine and sine?
Yes. But if you think about it, what other function relates sine and cos?
Tangent?
Tangent, right? So if I can get something in the form of sine x over cos x, I know that that's tan x, and I can use, and then I can work around that. That's the goal here. The reason why we did all this was because here then one could argue, why didn't I divide both sides by cos x in the beginning to get tangent? The problem is the arguments aren't the same. The argument of sine of x plus 60 is x plus 60, and here we have x plus 30. So to get the same argument, that's why we're doing all this trig business here. Okay, now if I move all the sines to one side, I'm going to get 3 over 2 sine x. If I move this to the other side, I'm going to get, so minus 2 root 3 over 2, which will give me minus root 3 over 2 cos x. Okay, now I need to divide both, I want to get the cos x on this side so that I can have tangent x. So I'm going to divide both sides by cos x. And I want to have this, the 3 over 2 on the other side so that I can find what that tangent of x equals. So I can multiply both sides by 2/3. And if I do that, the 2's will cancel. I'm going to get tangent x equals minus root 3 over 3. Okay? This, and that's the same as minus 1 on root 3. I think that's easier for me to see. And I know that that happens looking at, just thinking, visualizing the unit circle. I know that sine of, I need to have a root 3 over 2 in the denominator, which means I need to have cos as root 3 over 2. Cos of x is root 3 over 2 at pi over 6, I believe. Pi over 6 is how much? 30 degrees?
Yes.
Yes. No, wait. Yeah, 30 degrees. Cos would be root 3 over 2. Sine would be 1. Yeah, so 30 degrees. But the thing is, this is, I'm in, so the problem tells me I'm going from 0 to 180, but the problem is this is a negative. So if tan is negative, I have to be in this quadrant. I cannot be in this quadrant. So I start off with 30 degrees, knowing that that's the value at which I'm going to get. The sine of 30 is 1/2, and then cos of 30 is root 3 over 2. And the 2's will cancel, and I'm going to get 1 over root 3. Okay, sorry, I just need to confirm that for myself. So I know that this is going to be 30 degrees to get the positive value of that. So to get the other side of that, I'm going to do 180 minus 30, and that's going to imply that x equals 150 degrees. Do you see all these little steps here? You want to be really strong with your unit circle. Having that image in your mind and that symmetry is crucial to solve. I wouldn't even draw this on here. You're going to be wasting time. But you want to do enough problems where you get comfortable doing that. You want to have that image in your mind of that unit circle. That really, really helps. Okay? So this is a property. This formula is one you want to be really comfortable using. The sine A plus, like, you know, what I was telling you about earlier, right? That business. That's really useful. Okay, now let's look at part B. It's going to be literally like the exact same trig identity. You're going to use the exact same property. I think so. Just looking at the problem casually. So we're trying to show that sine of 105 degrees plus cos of 105 degrees equals 1 over root 2. Now, I don't know what it's going to end up being, but I do know, this is a paper one. I don't know how to solve 105 degrees. Do you know how to solve sine of 105 degrees from the unit circle? That seems very weird, right? That's like 90 plus 15. I don't know the sine of 15 degrees. Yeah, it's just a very odd angle, right? So what I want to do is I want to remember that I can use these formulas, right? If I know how to use these formulas, then I can break this angle up into something like maybe something like 45 degrees plus 60 degrees, because now I know I can use sine of 45 degrees and sine of 60 degrees. That's the goal here, is to take something complicated in what you don't know into something you can figure out. So I'm going to do the same for cos. And from our properties, we know that this is going to be sine A cos B plus cos A sine B, and then the other properties. So I'm going to go substitute straight in, and you'll see that this works out with the properties. Sine of 45 degrees is root 2 over 2. Cos of 60 degrees is 1/2. Plus cos of 45 degrees is root 2 over 2. Sine of 60 degrees is root 3 over 2, I believe. If you catch a mistake, please do tell me. Otherwise, this is going to be a mess. And then cos A, so cos of 45 degrees is root 2 over 2. Cos of 60 degrees is 1/2. But now cos, if you see the formula chart, cos of A plus B, the sign in the middle is going to be a negative. Okay? So now sine 45 degrees is root 2 over 2. Sine 60 degrees is root 3 over 2. Guess what happens? These two are going to go away because they're opposite signs, same magnitude. Now this is going to be root 2 over 4 plus root 2 over 4, which is simply root 2 over 2, which is none other than 1 over root 2, as required by the question. It's a very simple problem. It's nothing complicated. It's just you need to know how to use that identity. So once you know how to use that identity, it becomes very easy. Okay. Now, we want to look at part C. Part C doesn't look too bad either, but let's just give it a try. That way we're tying it back to complex. Because so far we haven't done any complex solutions yet. We've done trig. And trig is a big part of complex because the geometry also plays in, I think. Okay. So z equals 1 minus cos 2 theta minus I sine 2 theta. We're trying to find the modulus and argument. So the modulus of z is just the modulus of 1 minus cos 2 theta minus I sine 2 theta, right? Now, if you're really inclined, what you might do is go ahead and use the properties right now and say cos 2 theta equals 1 minus 2 sine squared theta. That's called a double angle identity. If you're on the chart, it's called a double angle. You could do that. I wouldn't do that. I like to use the Pythagorean because that's extra stuff for me to remember. I don't like doing that. What I like to do is go ahead and solve this. I know it'll look complicated at first, but you'll see it simplifies very nicely. Because this will be 1 minus cos 2 theta squared, quantity squared, plus sine squared 2 theta. Now, I know how to do algebra very well. I'm not very comfortable with trig identities, but something I am comfortable with is algebra. So let's do algebra. This is going to be a squared minus 2ab plus b squared, which is going to be plus cos squared 2 theta. Sorry, that should say sine squared 2 theta. I'm so sorry. And then plus sine squared 2 theta. Now, guess what? What is this? You should be able to recognize that. What would that be?
1.
1. Pythagorean identity. Pythagorean identity is one you should know. Like that's fundamental to all the trig identities. So now I know I'm going to have a 1 plus a 1. So I can write this as 2 minus 2 cos 2 theta. Now I have to end up using the double angle identity. I know because there's no other option. I have to in order to simplify this. So I can actually factor out a 2 here. If I have 1 minus cos 2 theta, I'm going to directly substitute this in. Your formula sheet doesn't have a formula for 1 minus cos 2 theta, but the formula is cos 2 theta equals 1 minus 2 sine squared theta. So if I move cos 2 theta to this side, I know that this is going to equal 2 sine squared theta on this side, right? So now I'm going to get square root of 2 times 2 sine squared theta. And now this is none other than 2 sine theta. That's the modulus of z. Make sense? Okay. All right. Now they want us to find the argument of z. Okay. So if we want to find the argument of z is going to equal arctan. And this isn't how they do it in the solutions. They start with saying tangent. The solutions in the mark scheme, I think they say tangent of theta, tangent of alpha equals y over x. But I like to do it this way, start with arctan, because that's my definition, how I have it in my mind. Arctan of y over x. Well, the y value is going to be what? It'll be negative sine 2 theta. And the value on the bottom is going to be 1 minus cos 2 theta. Okay. Now, this might seem like it's a lot to simplify, but once again, it's just a matter of trig identities. Okay, do you know, this is another one I'd memorize just because it comes helpful in AP calculus as well. What's sine 2 theta? Do you know what that is?
It's 2 sine alpha times cosine, or 2 sine theta cosine theta.
Yeah, 2 sine theta cosine theta. And you can actually, if you know the sum and difference identity for sine, you can easily derive that because it's sine A cos B plus cos A sine B. So this is just going to end up being 2 sine theta cos theta. And in the bottom, we have 1 minus cos 2 theta. Well, cos 2, we already figured out that, what am I doing wrong? I'm not doing anything. Never mind. Nothing wrong. I do this all the time. When I'm doing problems, I freak out because I think I'm doing something wrong. We're all good. 1 minus cos 2 theta, we already found out in the previous problem using that identity. You remember what it was? 1 minus cos 2 theta is 2 sine squared theta. So if I plug that in, 2 sine squared theta, guess what I get? 2's cancel. Sine of theta here cancels with one of the sines here. So I'm going to get arctan, and this is going to look really awkward, but It'll simplify out nicely at the end. Minus cos theta over sine theta. What's cos theta over sine theta? Cot theta, right? Cotangent of theta. If only that was a tangent of theta, we could have had a simple answer, but no, we have cotangent of theta. So when this happens, you can't leave your answer like this. When this happens, you just simply draw a right triangle and actually use the definitions of the ratios. So this is A, this is B, this is C. If I call this angle theta, okay? If I call that angle theta, cot theta is what? What would cot theta be? Theta, TOA, right? Tangent of theta is opposite over adjacent, TOA. So cot theta would be adjacent over opposite. It would be A over B. So now it's asking, what is the arctan of negative A over B, right? Because it's a negative cot theta. Which angle here will provide the arctangent of A over B? Well, if I pick this angle here, and I call that alpha right now, that's going to pick opposite over adjacent as A over B, right? So this is going to be essentially this angle. And I know that alpha has to equal pi over 2 minus theta because this is a right angle triangle. If that's 90 degrees, then these two must also sum to 90 degrees. That's pi over 2 minus theta. So now, because there's a negative out front, I know I have to distribute that negative because I know it's first quadrant is positive, second quadrant tangent is negative, right? Yeah, second quadrant tangent is negative. So I have to apply that negative. So if I know that arctan of A over B is alpha, which is pi over 2 minus theta, then I know that arctan of negative A over B, which is what the question is asking, is going to be theta minus pi over 2. You see how we did that? It's all logic. It's pure logic. There's no, there might be a little bit of trickery here, but yeah, it's not really trickery here. It's more logic. It's just walking through the step by step. If you're uncomfortable using the right triangle, like this idea of drawing out a right triangle and doing that, we use that a lot in trig substitution and calculus. But if you're not comfortable with doing that, then you might just want to start off by using other identities to reduce it down. And that's definitely possible. Nothing's impossible, really. Okay. Last part to this question. Hence, find the cube roots of z in modulus-argument form. We're going to find the cube roots of z. Okay, well, we already found out that z was going to be, well, we know the modulus of z, 2 sine theta.
Could you scroll back up to the question for 1 second?
Sure, of course.
Okay, thank you.
Hence, find the cube roots of z in modulus-argument form. Okay, all right. Also, 0 is less than theta is less than pi. I should have mentioned that for the problem we were doing earlier, because that would have, I think I did mention that, right? How it has to be in the second quadrant of the tangent. Anyways. Now z is going to equal the modulus, which was, I already forgot. Such bad short term. 2 sine theta times e, and please don't use cis. That cis notation is disgusting. I don't know why anyone would use that. No one uses that. Theta minus pi over 2. Plus 2 pi k, right? I can always add integer multiples of 2 pi. And I have to specify here that k is part of the set of integers. Okay. Now, what are they asking me to find? Samhitha, do you remember?
It was the
something root. Cube root.
Yeah.
Okay, cube root of z. Okay. So to find the cube root of z, I just take everything here to the 1/3 power. So I know I'm going to get 2 to the 1/3, sine to the 1/3 theta. I'm actually going to write it in cube roots here. That's 2 sine theta. Because there's no better way to write this. It's just, that is what it is. Now here, that's going to end up being e to the I. Theta, nope, no. It'll be e to the I. I'm going to take a common denominator here just so it makes things simpler. I'm going to take the common denominator of 2, and that'll be 2 theta minus pi plus 4 pi k, right? So now it'll be, if I divide everything by 3, because I'm taking it to the 1/3 power, it'll be 2 theta minus pi plus 4 pi k over 6. Okay? And of course, we need to test out those values. So the first value is going to be cube root of 2 sine theta. If we plug in k equals 0 here, we're going to get 2 theta minus pi over 6. E to the I, 2 theta minus pi over 6. That's the first solution. Second solution, once again, you just plug in k equals 1. You're going to get cube root of 2 sine theta times e to the, oh, sometimes it's auto shape filled business is really low. If I plug in 1 here, I'm going to get 4 pi. 4 pi minus pi is 3 pi. So I'm going to get 2 theta plus 3 pi. No, I did that wrong. If I plug in 1 here, 4 pi minus pi. Maybe I did it wrong in my, I think I did it wrong in my working over here. That would, yeah, if you plug in a 1 here, that'll be 4 pi minus pi is 3 pi. So 2 theta plus 3 pi on 6. And you could simplify that if you wanted to. Actually, I don't think you could. Never mind. Don't listen to what I said. Just said that. Cube root of 2 sine theta again. And if I plug in a 2 here, then I'm going to get 8 pi. 8 pi minus pi is 7 pi. So I'm going to get e to the I 7 pi, or 2 theta plus 7 pi, really. 2 theta plus 7 pi over 6. And that's your solution set for the cube roots. Okay? All right. Those, I think those two, if you can really solve those two, those are pretty good trig problems, both of them, the ones that we did. They're really good conceptual like properties, problems where you have to use properties. Let's try something from here. I think actually, to be honest, I think the older problems are the harder ones, in my honest opinion. Samhitha, Maham, is there any, just looking at these in random, is there any particular one that just draws your eye and you want to go to?
Maybe we could do, it says 11m.1.
This one?
Yeah.
Okay. 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 This one doesn't look too bad. Let's try it out. If you guys want to try it out and you guys want to explain it just for practice to say, feel free to do that. You can be like, Andrew, stop talking. I want to try it out. That's fine too, if you want to. Okay. So we have z cubed plus 1, and we want to factorize it into a linear and a quadratic factor. What do you think? What's probably the first option we can do here? Actually, this relies on a property. This doesn't even rely on a. This doesn't even rely on, like, I guess, like quadratic factoring methods that we know. This is actually a formula that you should know. Okay. If I have the sum of two, we learned this in algebra 2. Do you guys remember that? Sum of 2 cubes? Yeah. So if I have a cubed plus b cubed, that's equal to a plus b, and a square over here, ab over here, and b square over here. The way I remember the signs is it's SOO. Same, sorry, not even that, not SOO. It's same, opposite, always positive. That's how I remember. Same sign as here, opposite sign as this one, always positive here. Okay. The factorization is a plus b times a squared minus ab plus b squared. Okay. If I factorize z cubed plus 1, z cubed plus 1 is going to equal z plus 1 times z squared minus z plus 1. Easy as that. That gets you the point. Now, let gamma equal 1 plus I root 3 on 2. Show that gamma is one of the cube roots of -1. how can we solve this? What do you think we can do? How can we show that gamma is a cube root of -1? So if gamma is a cube root of -1, I can do what we've done in class, right? Where we write -1 in exponential form. So it'll be e to the I pi, correct? E to the I pi to the 1/3 power. But it says one of the cube roots. So I can't just write, I have to write e to the I pi plus 2 pi k to the 1/3 power. I'm taking the cube root. Make sure you specify that. Then you'll end up with e to the I pi plus 2 pi k on 3. And then once you do that, you can actually just turn this back into rectangular form. And the few solutions you're going to get, the first one you're going to get is, if you plug in 0 for k, you're going to get e to the pi over 3. What's e to the pi over 3? Cos of pi over 3 is 1/2, right? Cos of pi over 3 is 1/2. Then sine of pi over 3 is √3 over 2. It's going to be √3 on 2i. And that actually gives us gamma right there. But just for the sake of the problem, I'm going to solve the other two. I know that if I plug in a 1 here, that'll be 3 pi over 3. 3 pi over 3 is going to get me e to the I pi. And then if I do e to the I pi, the cos of pi is -1. And then sine of pi is 0. So one of the cube roots of -1, as we very well know, is -1, right? We didn't need to do complex numbers for that. And then finally, if we plug in k equals 2, we're going to get 4 pi plus pi, which is 5 pi over 3. E to the I 5 pi over 3 is going to be, that's 1 pi, 2 pi, 3 pi, 4 pi. 5 pi over 3 is going to be over here. 5 pi over 3, cos of pi on 3 is 1/2, so 5 pi on 3 is 1/2 over here, and then that should be a minus √3 on 2i, which makes sense, right? Because when we graph it, okay, sorry about that. So if I graph this, remember the roots of a complex number will give me points on a regular polygon, right? So that makes sense because one of them is going to be 1/2 plus √3 over 2i, 1/2 minus √3 over 2i, and that gives me that perfect triangle right there. Okay, so by doing this, we have shown that, well, we shouldn't have said gamma equals here. I would erase that. -1 to the 1/3 power. So we've shown that gamma, therefore gamma equals 1/2 plus √3 over 2i is one of the cube roots. And I would stop your answer right there. Because we've found all the 3 cube roots, so that's sufficient, I would say. So now we want to show that gamma squared minus gamma, equals gamma minus 1. How can we do that? How can we do that? Well, we know that gamma is one of the cube roots, right? If I square gamma, let's multiply both sides by gamma. Yeah, let's do that. I think that's how I would do this. I would start with left-hand side equals gamma squared. If I multiply that by gamma, well, I can't just multiply by gamma. That doesn't work. How would you do this? I'm a little bit lost here. Show that gamma squared. Do we just have to, maybe we just have to solve this as like a quadratic, right? If we know that, maybe I think that's what I would do then. Minus gamma plus 1 equals 0. Then I know that gamma equals -1, or sorry, +1, plus minus the square root of 1 minus 4ac, so minus 4 on 2, and that means the gamma equals 1 over 2 plus minus root 3 on 2I as required. And because gamma equals that, we've shown that that must be the case. I think that would work in the mark scheme, right? Gamma squared. Is that what we did here for part 2? Gamma is a root of then gamma squared minus, I think we did this one here. Did we? Actually, I don't think we did any of these.
No, we did. Wait, scroll down a bit. You did, what was method 2?
Method 2 is gamma squared equals.
Oh, wait, no, we didn't do any of those.
What did they, I'm curious by, how did they get gamma squared?
Oh, wait. We did method 1. Go back down.
We did method 1 here?
Yeah, because we did gamma squared minus gamma plus 1 equals 0. However, we didn't use z squared minus z.
Yeah, how do we know that z squared minus z plus 1 equals 0? Oh, I think it's because I erased it. We would have seen that if we, when we factored z cubed plus 1, remember that was z plus 1 times z squared minus z plus 1. And if we set that equal to 0, then you would immediately know that gamma has to be one of those roots.
Okay, yeah.
Okay, not bad, it's okay. And then find the value of 1 minus gamma. What is going on here? 1 minus gamma to the 6th power. Okay, well, we know that gamma is 1/2 plus I root 3. So 1 minus 1/2 is 1/2. And then minus root 3 over 2I is what I would put here, to the 6th power. And now there's no way I'm going to do binomial on this. So I'm going to write this in, doing this in binomial would take forever. So I'm going to write this in modulus argument form. So the modulus is 1 over 4 plus 3 on 4, which is 4 on 4. So the modulus is just 1 actually, which makes sense, right? Because that's what we've been dealing with this entire time. Modulus is 1. And then we have e to the I arctan of negative root 3 over 2 over 1/2. And if we do that, the 1/2, arctan of negative root 3. What is that? You know what that is? Root 3, sine of what angle equals root 3 over 2? In just the first quadrant.
I think, is it 60? I'm not sure. I don't have the.
Yeah, pi over 3. Yeah. So and that's the thing. Samhitha, like things like that, if you can like just recall those very quickly, I think that's gonna help you a lot, like on this exam, like on the entire IB exam. So that would be that would be pi on 3, but it's arctan of negative. So I need to look over here. So I have a positive x displacement and negative y displacement. So that's actually going to be negative pi over 3 in that case, because it's negative. Okay. And then all of that to the 6th power. And if I raise this whole thing to the 6th power, you will see that this very nicely simplifies to I to the negative 2 pi. And I to the negative 2 pi, well, negative 2 pi is just going back to where you started. So e to the I 0 is just 1. So this is going to be equal to 1, I believe. Sometimes I doubt my answers when they're so nice. Yeah, it's equal to 1. So they actually ended up using, doing binomial using all of this. But I think what we did also worked. Yeah, they did a bunch of other stuff. These are actually really elegant solutions, I think, what they did here. 1 minus gamma, and yeah, these are very elegant solutions. But I do think that what we did here would also work. Oh, I'm so sorry. Never mind. It wouldn't work because it says it says hence. Yeah, it says hence. So never mind. This solution wouldn't work. You can't do that. It wouldn't give you any credit.
But how do you know which method to use if they didn't? Like, I'm confused.
Okay. So whenever it says hence, you have to use something you've found out in the previous part of the problem.
Oh.
So if it asks you to find 1 minus gamma to the 6th power. Guess what? In the previous problem, we showed that gamma squared equals gamma minus 1. So 1 minus gamma is going to equal negative gamma squared. Does that make sense? So now I can just plug in negative gamma squared to the 6th power, and that's going to be what? Technically,
wait.
though, what we did could work. Why wouldn't that? Because they do give us gamma in the, anyways.
Wait, so if they say like, okay, so here we're doing negative gamma squared, right? So would we use what we found out in B2, that like gamma squared equals,
Well, no, I use that to get to here because I know that 1 minus gamma from this equation, that 1 minus gamma equals negative gamma squared. So I just plugged in negative gamma squared.
oh, so then would you put in gamma minus 1 there?
Well, now I would just say I can do gamma to the 6th power now, or sorry, to the 12th power now.
Oh, I see what you did. Okay. So basically, because in B2, it says gamma squared equals gamma minus 1.
Yeah.
You just did, okay. Got it.
But now what we have to do, I still think they want us to use what's in the previous parts of the problem. So I'm going to write this as gamma cubed to the 4th power. The reason why I do that is because I know that gamma is one of the cube roots of negative 1. If I cube gamma, it'll be negative 1. So now negative 1 to the 4th power, that's 1. This is actually an easier solution. So sometimes if it says hence, use what they give you, and sometimes it'll be a much easier solution. And I think that's what they ended up doing for method 1 here. Exactly what they did. Yeah. Okay, I think that was actually a really good problem to test all these skills. I think that was a nice blend of cube roots, of a bunch of those different skills. I think let's skip over, yeah, I think we're good with 1.5. Now let's go to 1.
Give me 1 second, I'll be right back.
Sure. I think I'm going to skip over 1.6 as well, just because we did an example with Modulus-Argument form. We've been using that when we were doing the cube root, so I don't think we need to re-go through that. And looking at the time, I want to make sure I don't spend too much time on stuff that you know how to do. Powers of complex numbers, de Moivre's theorem. We've done nth roots. We've done essentially this, so I don't want to repeat that. Conjugate roots of polynomial equations with real coefficients. I think that would be a good one to practice. So we'll do something from that next. And then for sure, we want to make sure to do something from the polynomials, right? So we're going to go to polynomials here. Okay. All right. I'm going to just wait until they come back, just so we can have a little bit of a break.
Right. Sorry, my camera's off, by the way. I'm like laying on my side now, so it's just a weird angle to have it on at.
As well. Okay. All right, Samhitha. So I decided to skip over 1.6 and 7 because we've essentially been doing this entire time. We've been doing Modulus-Argument form. We've been doing nth roots of a complex number. So okay. So let's go ahead and go to 1.8, which has to do with conjugates. And I think that this is a good problem because this reminds you to use certain properties as well, which is good. This has 5 marks. Oh no, this whole problem is actually probably way more. This is mathematical induction. This is from 2016. This was actually on 2016. I remember doing this. I'm not going to go through this because it doesn't make sense for the problems you already have access to. Let's do this one from 2009. Have you done this one yet? Does this problem look? No. Okay, let's do this. This is a very easy problem we can get real quickly. Okay, it's a cubic equation by the fundamental theorem of algebra. We know it has to have 3 roots, right? Whether complex or not complex. It'll likely be, it has to have, actually, because it's an odd polynomial, we know it has to have at least 1. So we know that z1 equals 2, z2 equals that, and those are the roots. So we know by definition from the lemma of the fundamental theorem of algebra that the z3 is going to equal 1 minus root 3i. right? Because conjugates have to be solutions as well. That's just something you need to know. Now, write down the third root. Oh, we've already done part A, which is great. And we earn a point for that. Okay, now find the values of B, C, and D. We need to find B, C, and D. So what I would do is we know that the factors have to be, we know by the factors, there's a factor theorem or something like that. I don't remember the names of the theorems. But if we have Z minus 2 times Z minus 1 plus root 3I times Z, there should be a parenthesis there, Z minus 1 minus root 3I, right? If I take all my roots and I like express them in factored form, that'll equal the original polynomial. So I'm going to find what this equals first. But in the beginning, actually, I would probably write something like this: z cubed plus bz squared plus cz plus d equals 0. Not equals 0 yet, but we know that that equals this because they're factors. Okay, so now it's a matter of FOILing out. So here we're going to have actually z minus 1 quantity squared minus root 3 squared I squared, which will be plus 3. Okay, I went through that kind of quickly. Do you see what I did here to expand these two out? This is just a difference of squares if you think about it. Right? Do you need help with that, or are you good with that part? Okay, all right. So now, once again, it's a matter of expanding out. So here I'm going to get z squared minus 2z plus 1 plus 3, which is a 4. If I FOIL this out further, I'm going to get z cubed minus 2z squared plus 4z minus 2z squared again from this one plus 4z and then minus 8. Okay, so this is going to be z cubed minus 4z squared plus 8z minus 8. Well, now we know what B, C, and D are. B is equal to -4. C is equal to 8. And then D is equal to -8. Does that look right? Okay, all right, let's look at the solutions. B equals -4, C equals 8, D equals -8. Perfect. And I think our logic holds true, so it's good. Okay. Finally, write Z2 and Z3 in the form RE to the I theta. That we know how to easily do, right? We've been doing that this entire time. So let's, okay, let's do this real quick. So Z2 is 1 plus root 3I. We know that what's the modulus of this? Of 1 plus root 3I. Let's do this in our head. Square root of 1 squared plus 3, which is?
2.
2. Yeah, well, square root of 4. Yeah, I know what you meant, Samhitha, don't worry. Okay, 2, and then e to the I, and then the theta. So the theta is going to be arctan root 3. Do you remember what arctan root 3 is? Arctan root 3 is going to be when sine is root 3 over 2, which is pi on 3. Okay, this is going to be 2e to the I pi on 3. While I'm taking my IB exams, I'm going to be like doing hand signs all, because that's how I visualize it. I don't care if people think that's weird, but honestly, that's how I visualize it. It really helps. Of course, really, if we already know what this is, then we can immediately find Z3, right? We know that Z2 equals this. So Z3, we don't even need to redo this whole process because we know that the conjugate has the same modulus, but the argument is reflected across. So it's 2e to the negative I pi over 3. Okay, let's look at the solutions. Negative I pi over 3, I pi over 3. Perfect. Good. All right, that was a nice and easy one. I think it's a good review of concepts, clarifies all of that. We're good with that. Okay. So now this is over polynomials. Is there a particular one? Let's try and pick something before 2015. Really, honestly, the earlier the better, in my opinion. The earlier ones are harder. I think I don't know why, but I think
The
that
08 one, the
this one.
yeah.
Okay. I wanted to do the next 08 one as well because I feel like that'll be a good question. And then I think we can wrap up for the night because it's been a while. Okay. Polynomial here is divisible. Okay, as soon as you see it's divisible, that means the remainder is 0. And if the remainder is 0, what does that mean? They're factors, right? There's two ways you can do this. You can either say x cubed. You can do it like we did in the last problem, where you set these equal to each other, and you say that this is equal to x plus 1 times x minus 2 times x minus r, where r is like the third root. That's one way of doing it. I personally don't like doing it that way because it'll take too much time on these types of problems, at least. Okay, so what I would do instead, one thing you can do is you can use the remainder theorem, right? You can use the remainder theorem and say because these are divisible, the remainder has to be 0, and the remainder is just p of that number right there, which is -1, because right, remainder theorem is x minus k, and it's negative. So I think you get the idea. If I plug in -1 here, I'm going to get -1 plus a minus b plus 2 equals 0. If I plug in p of 2, I'm going to get 8 plus 4a plus 2b plus 2 equals 0. And now I have an easy system of linear system of equations. I'm going to get on the top, I will have a minus b equals 2 minus 1 is 1, -1 on this side. And then on the bottom, I'll have 4a plus 2b equals -10. I'm going to multiply both of these by 2 just so it'll make it easier to eliminate. I'm going to get 6a equals -12. That means that implies that a equals -2. And if a equals -2, I can just plug it into an easier equation and say a minus b equals -1. That means b has to equal plus 1, which is -1. You see how we did that? That's much easier, right? Much easier way to do it than try and do the other method. Exactly what we did. I think that there's another method as well. Yeah, this is what they did. This is what, yeah, I wouldn't have done it this way. But because then you have to guess about the third root.
What did you get? B is equal to
Negative.
-1 and A is equal to -2?
Yeah.
Oh, you know what? I did it. I did it a way that I think might be a little easier too.
Okay, yeah, go ahead. Sure.
So what I did was, so I multiplied the x plus 1 and x minus 2 together,
Okay.
and then I got x squared minus x minus 2, and
Okay.
then on the other side I know I'm gonna have a x and then -1 because -1 times -2 is 2,
Ah,
and then
very nice.
yeah.
That's what they did for method 2 right here, the inspection by inspection. So I'm not good at that kind of stuff, but Maham, you're from the stuff we've been doing, you seem to be really good at spotting things really quickly. So yes, you know that that'll be a -1. So let me just write that in, and then you may continue. And then that'll be okay. Go ahead.
Oh, yeah. And then I'll just get x cubed minus 2x squared minus x minus 2, and then I know that my a value will be -2 and my b will be -1.
If you start off that way and you find that that's easier to do, I would do that. In general, just as a general tip, I wouldn't do that because then you have to guess about the third root, and sometimes you might not know what the third root is. So if you
Yeah,
see
yeah.
that, if you're able to inspect that, very well done. Okay. And here, what they're doing, I don't know what they're doing here. What are they doing? They're dividing the polynomial by that factor, and then, oh my, I wouldn't even try to. That's too much work. I wouldn't even try. Okay, well, we've done that. Let's go back, and there was another question here that I thought was pretty cool with the remainder. Similar question, and it relies once again on the remainder theorem. So let's take a look at this one. If it's divided by x minus 2, this time it's not evenly divisible. There's a remainder of 15. But it does tell us that x plus 3 is a factor. So what we can do is, first of all, if x plus 3 is a factor, that means the remainder has to be 0 when we divide it. That means f of -3, be very careful about that. F of -3, which is going to equal 81, 7, that'll essentially be minus 81, I believe, right? Negative 3 cubed times 3. Negative 3 cubed times 3 is negative 81, right?
Yeah.
Okay. And then,
yeah.
okay. And then 9p minus 2 times, so that'll be 6 plus q, and that has to equal 0. So that means we know that 9p plus q equals negative 6. Good? And then we once again use the remainder theorem, but with f equals f of 2 instead. F of 2 is going to equal 16 plus 24 plus 4p minus 4 plus q, and that's going to equal 15 because they told us the remainder is 15. So now we just do some shuffle-de with our numbers. I'm never going to say that again. That sounds so weird. Okay, 12 plus 24 is 36. 15 minus 36 is negative, oh my, 36 minus 15 is plus 24, negative 21, I believe. If this is wrong, this is going to screw the entire problem, but hopefully it's not wrong. So now we have our system, 9p plus q equals negative 6, and we have 4p. I'm going to make that a negative 4p, so I can eliminate the negative q then, and that'll be a positive 21. I'm going to get 5p equals 21 minus 6 is 15. P equals 3. And then using p equals 3, I can plug in p equals 3 here. 4 times 3 is 12. Negative 21 minus 12 is negative 33. I don't know. Negative 33 maybe? Yeah, q equals negative 33, p equals 3. This is just a matter of algebra at this point. Okay, but you want to remember the remainder theorem and be very, very careful about plugging in. If it's x plus 3, be careful about plugging in x minus 3. Or I mean, negative 3 into f of x. Okay. All right. I know all we did today was complex numbers. I know that stats and prob is going to be on there. Do you guys want to go through any of those problems, or do you think the last revise now was sufficient?
I think we're good.
Yeah.
Sorry, mine's echoing because say that one more time.
I'm good. I'm not sure. Maham, do you want to go over?
I'm fine too. Yeah. I don't need to go over it.
Awesome. All right. Do you guys want to go through any other problems, any other questions? Because otherwise, I think we're good for today. I think this was a solid session. We covered really everything there. I think you would need to know for this unit. Even trig stuff, really. Some of the geometry stuff we didn't do. Go ahead.
Just clarifying about like the wording of the problem. So if it says hence something, then you have to use something that you've already done. And then if it says like hence use blah blah blah, then you have to use that.
If it says hence or otherwise,
you can use whatever you want.
You can use whatever you want, but I would suggest if you look at the problem and you think, oh, I remember doing something earlier in the problem that will help me, use that, because that'll probably make it a lot easier. And then if you're like, I have no idea how this connects to the rest of the problem, then use another method. That's the benefit with hence or otherwise. But if it says hence, they're trying to make the problem easier on you. Like, don't think like this test is made against you. Really, to be honest, this test is really made for you. Like, think about all those questions, like, show that this equals this. If you didn't have the equal sign and the answer after that, like, they give you the answer. You just have to come up with it, right? So they give you half the battle most of the time. So just remember that, and I think that'll just give you some confidence. Really, once again, just take your time on this. I think if you try and rush, it'll just mess everything up. Just be true with each step. Have integrity with each step, and I think that'll, be what it is. Okay. All right, guys. Anything else?
No, I'm good. Thank you.
No, thank you for coming. All right. See you guys later. Bye.